Let's take our first look at Cython Plus actor system. So we're here in a Python virtual environment in which we have already installed Cython Plus and Jupyter Notebook, and we have already downloaded the Cython Plus standard libraries, especially the runtime, which is the actor system runtime. If you need to reach this step again, please refer to a previous video. So let's start a Jupyter Notebook. In which we have, again, the runtime and the standard library. And let's create a new notebook. So as always, we need to load the Cython Plus extension in order to use the Cython Plus cell magic. And we need to add this line at the top of the file. And we can get started writing our first actor program. So an actor is a unit of computation which can only be interacted with asynchronously. So it has some internal state, and it can receive messages and run some code based on the message. And it can send messages to other actors and even create new actors. And in this context, sending a message means calling a method asynchronously. In Cython Plus, there is no separate thing that is an actor as opposed to a SIP class. Every actor is actually an instance of a SIP class, and instances of SIP classes can be normal synchronous objects, and they can be turned into active objects which only interact asynchronously. And during its lifetime, an object can even go back and forth between being a synchronous classic object and an active object. So what this means is that to define an actor, we just need to define a SIP class. So let's do that. Let's call it greeter, because in this example, it will just print hello. And there is one small thing. We need to add the keyword activable. But this keyword does not mean that instances will be actors. It's not a separate kind of SIP class. It just means that instances of this SIP class may be turned into active objects. They don't need to be. The reason this is not the case by default for every SIP class is just an optimization to avoid generating code for asynchronous behavior all the time when it's not needed. So let's give this SIP class a field, call it identifier, and let's initialize it with a value inside the init method. Okay, and let's define a hello method that will take the GIL and print hello and something to let us know the ID of the greeter, like this. Perfect. So far we just have a basic SIP class, no actor here. This SIP class can be, so we can compile this SIP class can be used like a normal SIP class, also from Python. So I'm just going to do it quickly to show you that it works. Oops, of course. Perfect. Now, in order to turn this SIP class into an active object, we're still going to need some types from the runtime library. So we're going to need a scheduler, which will run the actor tasks. So its job is to map all the actor tasks onto a given set of system threads and do the job of scheduling. And we'll need a mailbox type, so a queue essentially, in which the actor will receive messages waiting to be processed by the actor. So the way the actor framework is implemented in Cython Plus is meant to be customizable by the user. So this is why we need to define the queue type. This queue type is defined for, this mailbox type is defined for convenience by the runtime, but actually the user could define their own version, and so we'll need to configure the actor to define which version, which kind of queue type should be used. And each queue type could have a specific behavior, but this is a convenient default that does what we want. So to set this this queue type, so to set this queue object that the actor will use, we need to use this hidden magic field. So this is the object that the actor will use as its queue. But first, the mailbox takes an instance, a reference to the scheduler as argument, because that way it can schedule the messages it receives onto the scheduler. And we need to add a keyword here, consume. So the reason we need to do this is in order to be thread safe, we need to be sure that only this actor has access to this mailbox. We don't want actors to be able to share mailboxes between multiple actors, because then they would be used on multiple threads at the same time, and it wouldn't be thread safe. So what we actually want is to be sure that this reference to the mailbox is the only reference to the mailbox, and in fact the only reference to any of its internal state. And the consume keyword is part of our type system for thread safety, and it does this. It guarantees that this reference is the only way to access any of the internal state of the batch mailbox. More on this later. So we have a scheduler, but this means we also need to create an instance of the scheduler somewhere. We could pass it as an argument to the constructor, but let's just create a global variable. So you'll notice this scheduler object has a scheduler type, but also a kind of type qualifier. And what this lock qualifier means is this specific instance can only be accessed by acquiring an object lock on it. The reason this is needed is because the scheduler is shared between all the actors, and it has some internal state that needs to be protected by a lock. And so we used this small part of our thread-safe type system to achieve this. But we don't need to worry about it because all the uses of the scheduler are hidden in the batch mailbox implementation. And now we can really use our SIP class as an actor. So let's define a main function. And let's release the GIL. And let's create a normal instance to start with. So create a 0. And let's create 3 of them, in fact, with different identifiers so that we can notice the difference. So we could just call the method hello on each one. Again, so far no actors. Let's call the main method to see what it does. hasn't compiled yet. Perfect. So now let's actually turn one of these normal synchronous objects into an active object. And to do this, we call them activate method, which takes as argument a reference to a normal synchronous object. But not just any reference. If we do it this way, it won't work. And the reason it won't work is we don't want it to work. If we do this, we have an actor that refers to the internal state of G0, but we still have G0, and we can still call hello synchronously on G0, and this wouldn't be thread safe. But if we run this, it won't compile. The reason it won't compile is because we need to add the consume keyword here again. The consume keyword will make sure that this is the only reference to any of the internal state of this object, and it will also basically delete the G0 reference. So after this, the only way to access the internal state of G0 will be A0. This also means that we may need to remove this line because now G0 doesn't refer to anything anymore. And now it compiles. So far so good. Let's now call an asynchronous method on this actor. So we call it hello again. This is an asynchronous call. There is one difference between the synchronous version of this call. We need to add an argument. Every argument is the same, except there's a first argument at the beginning that in our case we set to null. Since in our case there is no other argument, we only give it null. This is part of the customization points for the actor system. This could be an object that may be used to modify the behavior of the asynchronous call. But in our case, we don't need it, so we just set it to null. A kind of side effect of this is that it's easy to determine where the asynchronous calls are. It's all the calls that start with null as an argument. So if we now do this, we can compile it. And if we run the function, we have again called hello on every object. But this call is asynchronous. Now to prove to you that this call is really asynchronous, let's do the same for the second instance. And now we'll see that depending on the execution, the order of the prints may differ. Now that's almost it. One last thing before the end. I told you earlier that consume would ensure that this is the only way to refer to the internal state of these objects. Let's put this to the test. Let's say we wanted to cheat and we want to create an alias of G0, for example. So now we might think, hey, we can call g.hello, and this would access the internal state of G, which is G0, and this would also access the internal state of G0. But if you do this, it will compile, but at runtime, something will happen. I'll show you in a second. And what happens is there is a type error exception thrown by this keyword here. And what's going on is that since the the compiler was not able to prove at compile time that this is really an isolated reference to the only way to access the internal state of G0. It created a check that was executed at runtime, and this check uses reference counts to make sure that it's really the case and there's really no way to access any of the internal state of G0 other than G0. And clearly that's not the case because of this alias, and so that's why an exception was thrown. So this shows you how our type system provides some threat safety guarantees. And that's it.